Now it will be official. All right, so we'll start in about 30 seconds. And thanks for continuing to let others into the room, Ryan. I appreciate that.
Yes, and as everyone comes in, if you can put in the chat where you're from, as there's people from all over, we'd be interested to see where everyone's from. Welcome.
Yeah. All right, Jen, shall we start? What do you think?
Sure, yeah, let's get started.
Okay. All right, sounds good. I'd like to welcome everyone. My name is Peter Doherty. I'm the IBS Executive Director, and we'd all like to welcome you to the February Journal Club. How did we get to February? These sessions are complimentary to all IBS members with a primary purpose to provide a platform for individuals to present worthy papers in a public setting, and also to widen the scope of understanding for these papers. And we'll be hearing a very recent paper today from Biometrics, so I hope you enjoy it. Additionally, we want to provide a networking opportunity for IBS members through the Journal Club. So you're welcome to comment on what you hear today in the IBS members community. I have just a few general housekeeping comments before we get started. First, this session is being recorded, and that's one of the reasons your lines have been muted as you came in. And the recording will be available for replay early next week on the IBS website, biometricsociety.org. Please, if you unmute your line at any time, please remember to mute your microphone again and throughout the session. You will have an opportunity to ask questions during the Q&A period at the end. You may also ask questions via the chat feature, and we will address them during the Q&A portion at the end of the presentation, so later in this hour. But I'd like to now hand the program over to our chair of the Journal Club, Jen Lee from the University of Michigan. Jen, the floor is yours.
Thank you, Peter. So welcome, everyone. We're pleased to have Dr. Emily Hector joining us today to present her recent paper published in Biometrics titled Distributed Model Building and Recursive Integration for Big Spatial Data Modeling. So Emily is an assistant professor in the Department of Statistics at NC State. Her research concentrates on data integration, especially of correlated heterogeneous high-dimensional data, also in estimating equations and generalized methods of moments, as well as computational methods for distributed computing. We are also very glad to have Dr. Ben Seong Lee as our discussant today. So Ben is an assistant professor in the Department of Statistics at George Mason University. His research focuses on computational methods for high-dimensional hierarchical spatial temporal models, parallel computing, and uncertainty quantification. So he actually has joined us, our Journal Club lightning sessions last year. So welcome back, Ben. So all participants are encouraged to engage in the discussion and ask questions. We'll have Q&A towards the end of the session. So please, post your questions in the chat if you will during the talk, and you can also speak up towards the end. Okay, so without further ado, let's welcome Emily. So Emily, the floor is yours.
Thank you very much again for the lovely introduction, and thank you everybody for joining us. So can everybody see my screen and can everybody hear me? Perfect. Okay, thanks. So as Ken said, I'm an assistant professor in the Department of Statistics at NC State, and so today I'm going to be presenting a relatively short talk. We only have about half an hour related to a paper that was recently accepted and published in Biometrics. This is joint work with my colleague Brian Reach at NC State, as well as a colleague Annie at Brown University. The title of the talk today is Distributed Model Building and Recursive Integration for Big Spatial Data. Because this is a short talk, I'm going to omit a lot of the finer details, but of course, if you're interested, feel free to check out the paper. I'm also really happy to correspond via email. I'll have my contact details at the end. Really happy to chat about anything that I've presented today, either in the Q&A or via email. I'm going to start with our motivation to kind of drive the particular method development that I'm going to present today, which is related to functional connectivity. So I'm assuming that most of you are familiar with what is called an MRI machine, or a magnetic resonance imaging machine. And the idea is that a person would lie in this machine for a period of time. They're asked to think about too specific. So this is what we call resting state functional MRI. And the MRI machine is measuring blood oxygenation as blood is flowing throughout the brain. And so the idea is that blood is being sent to regions of the brain that are being active or activated during rest, and that this kind of characterizes intrinsic brain activity in the absence of a stimulus or so that's kind of the data that we're looking at. And then the particular focus here is on functional connectivity. So the idea is that as blood is flowing to different parts of the brain and oxygen is being carried and is being captured by the MRI machine, we can use correlation between these different signals to try to tell us about which parts of the brain are functionally connected. So if two parts of the brain are kind of lighting up simultaneously, then we think that these parts of the brain are functionally connected. They're performing a similar function. And so at a very coarse level, what this might look like is the picture that I have on the top here. So my first part, in part A, I have 3 different slices of a person's brain, and I've overlaid what's called an atlas on top, and that atlas is telling us which parts or which voxels or pixels in their brain belong to specific brain regions that are known in advance and annotated within the atlas. And so this is denoted by different colors in the brain. And then to try to characterize functional connectivity between these different parts of the brain, these different brain regions of interest, or these ROIs, we average the time series across all of the voxels within each of these brain regions of interest. At each time point, we take an average over all of the voxels or the pixels within that brain region, and we create what we have in panel B here, which is this average time series, and it's the average across all of the pixels within a particular brain region. And so typically there's about 200 brain regions, maybe 500, depending on the atlas. And then we take cross correlations across all of these time series, treating the time points as roughly independent, to obtain a correlation matrix that looks like what we have in panel C here for each individual participant. And so each element of this correlation matrix is telling us the correlation between the average time series in 2 different brain regions. And therefore, it kind of represents the functional connectivity between those 2 regions in the brain. So functional connectivity is kind of the particular data type that we're going to be looking at, but really the biological question that we're interested in is motivated by a study of autism spectrum disorder, or ASD. So there's been some emerging evidence that has shown that autism can be broadly characterized as a brain disconnection syndrome, and that's disconnection with a Y. So what that means is that people who have autism exhibit patterns of functional disconnectivity, or patterns of connectivity that are either higher or lower than their typically developing peers. So parts of the brain are more connected or less connected than people who do not have autism. And the way that, for example, this might work is I'm illustrating here with just 2 particular brain regions. I've taken the left and the right precentral gyri here. We might average the time series across all of the voxels within these 2 brain regions and obtain these 2 time series. And then we take this cross correlation just like I showed you on the previous figure, but now I'm only looking at 2 brain regions, so I just have a scalar. So this scalar is the correlation between these 2 brain regions for this particular individual, and then we might regress that onto some participant level covariates such as age, sex, and age and sex, as well as a particular autism spectrum disorder status. And so the question is whether that autism spectrum disorder status is significantly associated with the correlation between these 2 brain regions that might allow us to say whether or not this pattern of connectivity is higher or lower than somebody who doesn't have autism. So this approach has actually worked pretty well, but one of the main challenges that has really emerged is that findings have varied a lot across different studies. And so there isn't a general consensus on which brain regions in autism exhibit these particular disconnectivities. There's kind of some general patterns, but there's been a lot of difficulty in trying to replicate these results across different studies and trying to figure out what the consensus is on which brain regions exhibit these functional disconnects. And so one hypothesis that we have for this difficulty in generating the consensus in the literature is that by taking this average time series across all of the voxels within this region, we're actually obscuring a lot of the important variation across all of the voxels within each brain region. So we're essentially performing this pretty strict dimension reduction by performing this averaging. And so we're really potentially losing a lot of the variability and also reducing a lot of our statistical power to be able to examine this particular association. And so this is really going to motivate us to start to think about how, instead of doing this averaging that I'm illustrating in this middle panel here, instead, perhaps we could use the voxel level data or the pixel level data and do a multivariate analysis. So that instead of having a scalar here, I might have all of the cross correlations between these two brain regions and try to understand how those change with respect to participant level characteristics, including autism. And so I'm going to start to set up a little bit of notation here for what this might look like. So for each of my capital N participants here, I'm going to let my yi of s be the rFMRI time series that had a particular voxel s or particular location s. And these voxels that I'm going to look at in my particular motivating example here, I'm going to really narrow my focus to only look at the left and right precentral gyri. This is primarily for illustration purposes. This would not be difficult to generalize to other regions of interest. And I'm going to denote by script D here the set of all of my voxel locations in my left or my right precentral gyri. And so now, instead of performing this averaging, like I showed you on the previous slide, what I want is to look at all of the cross correlations between all of the voxels that are in the left or the right precentral gyri. And so what I'm showing you on the right-hand plot here is what all of these cross correlations look like. And so visually, this should look like not much to you. And that's actually kind of the point, right? There's a huge number of functional connectivities or a huge number of correlations across these two different brain regions. And that's going to be a real challenge from a computational perspective. So in order to start to build my model, let's kind of talk about some of the assumptions that we're going to make. I'm going to assume that the resting state time series here is distributed following a Gaussian process with some additive independent Gaussian noise that has a variance of sigma squared. The Gaussian assumption here, there's kind of some background for why this is reasonable, but all I'll say at this point, right, is that it's a fairly reasonable assumption for these particular data and how they were collected. And then for each of my participants, I'm going to assume that I observed some explanatory variables. Again, this is autism, age, sex, and maybe some interaction terms as well. So my Gaussian data are being observed on each and every single participant and each and every single voxel in my left and right precentral gyri. And I, in addition, have these participant level features. The mean of my Gaussian process, I'm going to assume that this is simply a constant mean, and that's because the mean of my time series here is not particularly meaningful on its own due to interscanner differences, and so my data are mean-centered and standardized, and so the mean here is simply assumed to be a scalar that should ideally be pretty close to zero. The real focus is on the covariance between the time series. Remember that that's the functional connectivity. That's really what I'm interested in modeling, is the correlation between the time series at different voxels. And so I'm going to model that here using this fairly complicated looking model. This is a modification of a covariance model originally proposed by Pacherek and Shervish. The modification that we're making here is to introduce our covariate effect, because what we want to be able to estimate is how covariates, including autism, influence the strength of the correlation between different regions in the brain. And so you'll notice here that I have in the denominator these rho ij's and ij primes, and this is how we're modeling our covariate effect, so that the strength of the dependence is a function of those covariates through this parameter that I'm going to call rho here, rho sj. And so altogether, the parameters I'm going to try to estimate are the mean. These rho SJs, those are really the parameters I'm most interested in carrying out inference on. because they're going to tell me how autism is influencing the functional connectivity between different voxels in the brain, as well as this error variance sigma square. So this is my model. And so if I just kind of put down what a Gaussian likelihood might look like, you'll have the following equation here, which should hopefully look really familiar to everybody in the audience here. And so in the plots that I've shown and kind of the setup that I've described here, it's hopefully clear that I have a lot of data. So I have a lot of participants, and for each participant, I have measured these time series at a large number of voxels. I have about 11 gigabytes of data, which is not that unreasonable. I can load that into R and it would work just fine. The main challenge is in the calculation of the likelihood. In particular, the covariance, which describes the functional connectivity, which I'm primarily interested in carrying out inference on, which is this sigma I matrix here, I for participant I, is very large, and it has a very large number of entries. It has, in fact, on the order of 13.5 million entries, because it's looking at all of the correlations between any two voxels in the left and right precentral tract. And so anytime that and because it's a participant level covariance matrix, I have to compute 13.5 million entries for every single independent participant in my study, which is going to give me on the order of 279 million entries that I'm going to have to compute every single time. And that's a lot of data, right? So it's not necessarily the data that are large, it's really the fact that I have this covariance model, which is really going to drive the computational costs. And so anytime that I'm going to have to store this matrix, I'm going to need huge computational resources just to store it. And anytime I need to invert it, I'm also going to need huge computational resources to invert this covariance matrix. And in fact, I'm going to argue that it's not really feasible, and I'll show you a little bit towards the end exactly what I mean by not feasible. So today I'm going to talk about how we can estimate and do inference for these mean and covariance parameters. And we're going to do this within a distributed framework or a divide and conquer framework. And the approach I'm going to present here is there's a really strong emphasis on a method that is both computationally efficient as well as statistically efficient. And by statistically efficient, what I primarily mean is really leveraging all of the information to have small standard errors. The key ingredients of the method I'll present are first spatial partitioning, right? That's kind of in the name, distributed framework, a divide and conquer. So I'm going to have to divide, so I'm going to partition my domain. Then I'm going to talk a little, very, very briefly about how to combine those estimates, and there'll be a connection here to the generalized method of Smallman's. And then I'll tell you about how this actually doesn't solve all of our problems, and it's actually still quite challenging to do what I've proposed so far. And I'll introduce something new that will rely on some optimal estimating function theory, as well as kind of some projections of our estimating functions into lower dimensional spaces, so that we can have something which is computationally and statistically efficient. So this is broadly speaking the road. So let's start with the first ingredient, our spatial partitioning. So I'm going to illustrate this on just a two-dimensional domain, because it's pretty hard to plot these things in a three-dimensional space and to show you how things are partitioned. So just try to imagine that this two-dimensional surface here is actually something that's from the brain, okay? So I know that it's a little bit of a simplification here, but this is primarily for illustration. And so what I'm going to do is partition this spatial domain into roughly equal-sized blocks. Here they're actually perfectly equal, that are 10 by 10. And I'm going to partition my entire domain here according to what I call nearest neighbors, meaning that the locations that are closest to each other are going to be in a single block or a single little square here. And then once I've performed this partition, I'm only going to consider each of these small squares. So in my brain imaging example, I'm going to take all of my voxels in my two different regions of interest, and I'm going to partition those regions of interest to only look at a very small number of voxels. And then because I'm only looking at a small number of voxels or a small number of locations, now my likelihood is going to be very tractable. So instead of looking at my full data set, I'm only going to be looking at these partitioned data sets for these very small blocks of data. And so because they're so small, the likelihood is tractable, and I can get my maximum likelihood estimator relatively computationally efficiently. And ideally, I can get all of these estimates in parallel to really maximize my computational efficiencies, to make things really, really fast. And then I'll also compute this quantity, which will become relevant later, which is the derivative of your score function or your Hessian. And so what we're at here is this point where I've taken all of my different blocks and I've analyzed them all separately and in parallel really efficiently using maximum likelihood estimation. And I get estimates of my, in particular, my mean, as well as the association between autism and brain functional connectivity, as well as my nugget variance. And then I also collect these other summary measures that are going to be relevant for computing variance. So at this point, everything has been really, really fast. And so the question is, how do we put all of these estimates together so that we obtain a unified inference over the entire data set or over both entire brain regions of interest, the entire left and right precentral gyri, and not just these small groups of blocks. So in trying to combine things, what we're going to do is take our score functions and stack them one on top of the other. And then we're going to calculate the sample covariance matrix of those score functions. We'll call that V hat. And it turns out that through some arguments, you can actually show that this V hat is capturing the dependence between those different blocks of data. It's capturing the dependence between the different groups of voxels that you have partitioned and analyzed separately. And so if we take a weighted average of all of our block estimates, we weight it by this inverse variance function here, and then we put a scaling factor in front, we can obtain a combined estimator that is now taking into account the estimates from all of the different blocks, as well as their cross covariances across the different groups of blocks. There's a connection here to the generalized method of moments that I promised. I won't have the chance to talk about it, but essentially the generalized method of moments is an approach for over-identified parameters, like my parameters data here, which is over-identified by all of my different blocks, and it minimizes the quadratic form of these estimating functions. That quadratic form, if we use this particular weight matrix, is what is called Hansen efficient or Hansen optimal. It basically just means that it's very statistically efficient. And then this estimator that I'm proposing here is asymptotically equivalent to that estimator from the generalized method of moments. So all of that to say that there's a connection to some other methods here that allows us to say that this estimator is very statistically efficient, and it's also very computationally efficient. So it's computationally efficient because what I've done is analyze small blocks of data in parallel very quickly. And then I've essentially plugged them into an average formula that allows me to obtain a unified inference over all of my different groups of voxels. And so this final estimator here is the final estimator over the entire domain that I was interested in. So everything's great. It seems like we've solved our problem and we can estimate these parameters of interest in this computationally and statistically efficient framework. And so now we arrive at that third ingredient, the one where I mentioned that there was, I would tell you that I hadn't solved my problem and that things would actually be a little bit challenging still. So it turns out that this weight matrix that we have to invert in order to put inside of our average, it turns out that its dimension can still be very large. And the reason for that is that its dimension depends on the number of blocks that you have in your partition space. And so you can imagine that if the number of locations is truly massive, in order to partition a truly massive number of locations into small blocks so that the blocks remain really small, you're going to need a lot of blocks, right? If I take 10 million and I want to divide it in such a way that my unit is 25, I have to divide by a very large number. And that very large number here is this KM. And that's pretty problematic because now this matrix is very large, even for a moderate number of parameters that I'm trying to estimate. So worst case scenario, this matrix here is the dimension is actually larger than the sample size, in which case it's not full rank. But even if that's not the case, even if it is actually smaller than this capital N, the fact that I have to invert it is going to pose some computational challenges. And so this approach to combining everything together, while it may look that it's really solved the problem, the issue remains in truly high dimensional settings that the number of blocks is going to remain quite large, and therefore we cannot avoid the entire computational cost of doing it. So what I'm going to propose instead is a way of essentially analyzing everything in the same way that I did in my first step. So partitioning everything in the same way that I have right here. And I'm going to modify the way that I'm going to start to combine things. And the way that I'm going to modify that is by thinking about all of these different blocks as being nested inside of a recursive partition. So instead of taking my domain on the left-hand side and splitting it immediately into what I have on the right-hand side, I'm going to take a more a recursive approach to partitioning my spatial domain. So what's that going to look like? So I'm going to start with my domain on the left-hand side here. This is what I'm going to call resolution 0. And then at the first resolution, I'm just going to divide it into 4. So I have 4 blocks, 1, 2, 3, 4. And then at the next resolution, I'm going to take each of those blocks and divide those into 4. So now I'm going to have a total of 4 times 4 blocks. But I'm thinking about these 4 blocks right here as being nested within this larger block with the black line. So that's going to be at my second resolution, and I can keep going. So at a third resolution, I'm going to take each of those blocks and divide again into 4. And then at the next resolution, I'm going to go again, and I'm going to take each of these blocks and I'm going to divide into 4. And it turns out that if you look at this partitioning scheme, it's identical to what I had shown you earlier, except that we're now thinking about these 4 blocks as being nested within this larger block, which is itself nested within these larger blocks, which are themselves nested within this larger. And so instead of thinking about how to combine everything at once, we're going to think about how to combine these small groups of blocks a little bit at a time. So in my first stage, I'm still going to have all of my different blocks that are going to come from this partition data set. I'm going to analyze them just like I presented earlier using maximum likelihood in parallel, and this is going to be really computationally and statistically efficient. But then the real difference is going to be how I combine the estimators. And so instead of combining these all together at once, I'm only going to combine them 4 at a time. And I'm going to form some combined estimators that are not combined over the entire data set, but combined over some groups of plots. I can keep going and so on and so forth. And so the real question is, how do I actually perform this recursive integration? And so the problem is that if we continue to stack our equations one on top of the other, the dimension is going to continue to grow and grow and grow, and things will get really computationally expensive. And so this is that third ingredient that I mentioned, where we're going to project some estimating equations into a lower dimensional space before stacking. So because this is a really short talk, I'm not going to have a chance to tell you exactly how this works. But the main idea is just that instead of allowing the dimension of the estimating function to grow at each combination step, we're going to reduce its dimension through this projection step in a way that's statistically efficient using variances of your estimating functions. So I'll skip over the mathematical details. They're all in the paper. But at the end of the day, what we end up with is a combined estimator that looks like the one on the bottom here. And I personally think that this figure illustrates it a little bit. So at the bottom hierarchy, you have all of your different data sets, and you're going to combine your 3 data sets over here into one estimator at this level. You'll have to go back to the bottom layer to compute your weight matrices for that projection step. And then you're going to combine these 2 estimators into this one and these 2 estimators into this one. And then at the final step, you'll combine these 2 estimators into the final step, into the final estimator here, which is over the entire spatial domain that you were interested in analyzing in the first. So this is what I mean by this recursive integration, where instead of combining all of the estimators together immediately, we're really just kind of pinching the different blocks together and creating these intermediate estimators that are computationally and statistically efficient. And so at each step, the size of any inversion that I need to handle depends on the number of blocks at that particular step. So in my earlier figure, that was 4. And here it's also 4. The number of blocks here that I'm combining is 4. And so that's going to be much smaller than what I had presented as the alternative earlier. There's a lot of math that we can do to show that this works. We get an estimator which is consistent, it's entirely Gaussian, we can estimate its variance. But my main point that I want to try to convey to you is that this is really computationally efficient. And I think that this is best illustrated with a very, very short simulation that I'm going to tell you. So my domain here is very small. I'm just looking at 400 spatial locations. It's a 20 by 20 domain that I'm going to partition first into 2. And then each of these halves will get partitioned again into 2. And then each of these quarters will get partitioned into 4. So this is a kind of this recursive partition that I've described here. and I have about 10,000 independent records. So just briefly looking at some measures of the statistical inference, I'm looking at here asymptotic standard errors, empirical standard errors, and root mean squared errors, and I'm comparing to the nearest neighbor Gaussian process, which is kind of the state of the art in this field, as well as a partitioning approach that ignores the dependence between the different blocks. And then this is 3 different ways of combining that we're proposing. And so I just want to show you here that the statistical inference that we get is comparable to the state of the art from the nearest neighbor Gaussian process in terms of both the measure of statistical efficiency, the variance, as well as the size. But the real advantage is the computational gain. So our approach takes about 80 seconds on average, whereas the state of the art takes 280 seconds. So it's about 350 times slower to use the state of the art. And that's, kind of inherent to the NNGP approach, in the sense that they are dealing with the whole data. And so even if there's a lot of sparsity in the covariance matrix, which is one of the assumptions of the NNGP, it is still handling the whole data. And so there's only, there's a limit to how fast it can be. Whereas by handling only small blocks of data, we can really get a massive computational gain. And these computational gains will be even more substantial when we model these participant level covariance matrices like I have in my data. So in my last few minutes here, I want to return to my data analysis and show you kind of what this gives us. So you'll recall that I was looking at the left and the right percentile gyri. As my covariance, I have an intercept. I have my autism spectrum disorder status. This is really the covariate of interest that I'm trying to carry out inference for. I have age, sex, and then an age by autism status interaction. I'm going to take all of these voxels and I'm going to partition them in that recursive scheme that I've introduced. And I'm going to partition it using 3 different resolutions. So first, I'll split them in half. Then I'll split each of those halves into 4. And then I'll take each of those components and split it again into 4. And then I'm going to use the procedure that I've described to estimate my parameters and then to combine in this recursive scheme. And so these are the estimates that we get. I'll describe them in a little bit more detail on my next slide, but essentially what this is saying is that there's a negative association here between autism spectrum disorder and the correlation here within both my left and my right percentile gyri. But the main point I want to highlight is actually down here. So our approach, if we parallelize across 32 CPUs and we use 4 gigabytes of RAM, very small, takes 5 hours. A referee asked me to try to run the full maximum likelihood, and I tried. I had to request more than 175 gigabytes of RAM, and so that's because you're trying to store that full covariance matrix, even though we use sparse covariance matrix data types to do this, and the computation timed out after 190 hours. So we never got results using full maximum likelihood inference, and so I think that this really highlights kind of the fact that this is a problem that was not just difficult, but infeasible before. And our approach has brought this down to something that can be done within about 5 minutes. So trying to interpret these effects, so we found that there's actually no difference in the correlation of the 2 ROIs according to autism and autism by age interactions. And so what that means is that the 2 ROIs are kind of behaving similarly in their association with autism and this interaction. And we find that autism manifests as hyperconnectivity, both within and between the right and left percentile gyri. So that means that people who have autism spectrum disorder have higher levels of functional connectivity than their typically developing peers. And just as a point of comparison, so these findings concur with some of the existing literature, but we went back and we looked at that less powered traditional approach, which does this averaging of the time series across all of the voxels, and the point estimates are actually really, really close. The primary difference between our approach and the less powered approach, as you can imagine by the name, is that we have much smaller measures of the uncertainty. So we have much more efficient inference. And so we can make statements with a lot higher power than using this traditional. So I'll just conclude here by, of course, mentioning that there's no free lunch, right? So there are some limitations. So a question I always get is that, how does this depend on the choice of the partition? And so the answer is it does. It depends on how you partition your data. We did a bunch of checks, and as long as you use a reasonable partition, and by that I mean that you're partitioning things according to these nearest neighbor locations, as long as the number of locations is not too large, not too small, And as long as you have a range of spatial distances within the block, things are reasonable and they don't change, the results don't change too much according to how you partition your data. There's some literature that talks about different partitioning schemes for the Gaussian process, which we cite in that paper. And so, but this is always going to have to be evaluated on a case-by-case basis. Something that's a little bit not traditional here relative to spatial analyses that are more frequent in the literature is that all of our asymptotics are in the number of independent participants. So we here are deriving all of our consistency results, for example, assuming that the number of independent participants is growing or is, very, very large. And this is different from your more typical spatial analysis where asymptotics would be under a diverging domain, for example. Here, we've allowed our theta parameter to vary spatially in a very specific context. What I allowed was for the autism effect to be different within the two brain regions. It is possible to extend this to have a more general variant coefficient model using some of other work that I've done, but I assume that the math would become quite complicated, but I think it's feasible. And then also we've proposed this covariance model, kind of this extension from the Petrarch and Chervish paper. I think that there are also more flexible modeling approaches for the between ROI correlations that could be explored, but that were beyond the scope of the present paper. So with that, I'll wrap up. I'm going to turn it over to Ben, I think, but I'm happy to take questions during the Q&A as well. And also feel free to contact me. I'm happy to take questions via email. Thanks very much.
Thank you, Emily. Very nice presentation. Particularly appreciate you provide the insights at the very beginning to set up the motivation for the work. It's very nicely presented. Thank you.
Thank you.
So next we'll have Ben discussing the work and also have some extensions. So Ben, please feel free.
Good. Let me just do this full screen. See if everyone can see. Okay. All right, Emily, thank you very much for a wonderful talk. I actually had a really great time, not review, I didn't review the paper, but like just going through the paper and it really like opened up my eyes to different ideas that I wasn't, privy to before. And it was a very fulfilling exercise for me to put this discussion together. So I'll do my best to kind of summarize the manuscript. So I think it's always like nice to start off with the scientific motivation because a lot of interesting papers typically have these strong motivations. So the key thing here was to look at brain functional organization between people with autism spectrum disorder and those who are neurotypical. So the idea here is that can we use existing spatial models based on Gaussian processes to understand the functional connectivity in the brain? Now, as Emily mentioned, the major challenge here has to do with computation and storage. When you're dealing with high-dimensional multivariate normal densities, which are key to these spatial models, you end up seeing computational costs that increases cubically in computation and quadratically in storage. So the proposed methodology in this manuscript uses this multi-resolution recursive integration, and I think it's very neat because it really kind of bypasses some of the heavy computation that is inherent to these spatial models. So first, the spatial domain is partitioned into this many subregions. So this is the product of KM, where M goes from 1 through the highest resolution, big M, with big M resolutions. And as I think it's a little difficult to see here, but I'll zoom in. So here at the 0th resolution, this is the full spatial domain. And for each resolution, you are essentially partitioning these into different like structures. So they're you're creating these like disjoint subregions. Now here, the nice thing about this method is that we're doing global inference of our model parameters theta using the generalized method of moments. And what you'll see is that we're going to be living in the zone where we're dealing with the small, like the highest resolution partitions. So in this methodology, there is this recursive integration where inference at the lower resolutions are actually built upon the inference done at the higher resolution that's one step ahead. So the resulting estimators, we end up getting these two consistent recursive estimators denoted as theta hat R and theta hat S that integrate inference over all sets and all resolutions. Now, what I think is very neat is that this thing is very fast because it bypasses these like very expensive covariance matrix operations, especially these inversions, and the full computational complexity that's reported on the in the paper is as follows. And from this, what I notice is the computational complexity. Yes, it is determined by the number of resolutions and the number of subjects that you have, but these are the cubic elements here. Since the method deals with like the number of locations in the smallest partition, this value can be chosen to be very, very small. And then this Kmax can also be chosen to be relatively small to help computation. It's also very scalable because there are embarrassingly parallel operations that can be distributed across cores. And based on the paper, a single core is dedicated for each of these smaller subregions. The method is demonstrated on multiple simulation studies. I very much appreciated this because you're looking at simpler stationary models, as well as models that deal with large number of locations, models that include transformations to the data, and a special case that mimics the application. I really like that they compared this to the state of the art, including nearest neighbor Gaussian processes, which use a sparse covariance and precision matrix, as well as the partitioning method done by Ethan et al. And then the application is done on, looks at brain connectivity and autism brain imaging data set. Okay. Right, so it examines brain connectivity, and it's nice because it actually, the results of the study answers this question. So we really circle back to the motivational problem. So based on this, like one thing I would like to say is that this method is very embarrassingly parallel. It really leverages the distributed computing that's available. And I just want to point out again that the computational complexity scales with really it scales with the size of your smallest partition. Just to put it into perspective, there has been different scalable approaches that have been used to fit different types of different types of hierarchical spatial models. These include basis representations, sparse covariance and precision matrices, which include the nearest neighbor Gaussian processes here. The basis representations actually do a dimension reduction where instead of modeling a high dimensional spatial process omega, you can approximate it using a basis expansion where B is your basis functions and delta can be a lower dimensional set of spatial coefficients. Another set of models that have been used are conjugate spatial models, at least in the Bayesian framework. These models have also improved computation by giving you easy conjugate distributions, or allows you to perform like Gibbs sampling much easier. Okay. Now I'd like to kind of go over some of the divide and conquer and subsampling approaches that have come up recently, because I think this is very much tied to the study at hand. So the idea here is that you're trying to fit these spatial models either using subsets of the data or subsampling. Now, for many of these, many focus on kriging or interpolation or predictions at unknown locations, as opposed to global parameter inference that this manuscript examines. So the first is local adaptive Gaussian processes. This is done in the computer experiments literature, and it really looks at the local predictions by selecting subsets of nearby training points. And the size and shapes of these local neighborhoods are determined dynamically. Another one is spatial metakriging. Here, the data is partitioned into different subsets, and we're going to fit a spatial model for each of these subsets. Now, after a spatial model is fit on each of these subsets, the results are combined using a geometric median that gives us a approximate global posterior distribution that basically like combines the individual posteriors. Spatial data subset models use subsampling within an MCMC algorithm. So instead of modeling your entire data set so instead of sampling from the posterior using the entire data set, there is an inclusion vector that acts as a parameter in the model that actively or dynamically subsamples the data. So it makes the MCMC algorithm run faster. Now, this is a shameless plug for a manuscript that me and my collaborator wrote a while back. This is also a different subsampling approach where we're partitioning our spatial domain into k different subregions, and we're going to fit local semi-parametric methods on these k subregions, and then the results are tied together using local weighting processes. One study that I do want to point out that that has been used in the climate modeling literature is this ExaGeostat that has been done by the folks over at House. This is where they use parallelization and distributed computing through HPCs to optimize the likelihood functions for high-dimensional spatial models. This is on the scale of millions and millions of data sets, so they're able to generate massive synthetic data sets that mimic weather models. And this manuscript that we discussed, Emily's manuscript, I think it's a very nice inclusion to this like subsampling methods, because it really looks at global parameter estimation. Many of these are focused more on kriging or prediction, but this parameter inference sometimes gets put on the back burner or somewhat neglected. Yeah. So some extensions that I'd like to point out. One example would be extensions into non-Gaussian data. I'd like to bring up computational complexity here. So the one thing that computational complexity is dependent on is this P, which is the number of parameters that are estimated. In this study, it was typically the correlation parameters and then your regression coefficients in the model. What happens when you're dealing with something like a binary spatial model, where you have these spatial random effects, omegas, that all must be estimated? A lot of time, these omegas are in the order of n, really. In that case, that would really increase the number of the P here, and that may drive up computational complexity to the point where it could be infeasible. So some possible ideas to get around that is maybe you could reduce the dimensions of these omegas. So instead of estimating all of these omegas that are in the model, can you slap on a set of global basis functions and instead model these deltas, which could be much smaller than the omegas, thereby driving down this P number. Other extensions that I've thought about when reading this is, are there other types of non-stationary covariance functions that one could examine? For example, this study looks at a modified version of the Paciorek and Chervish non-stationary covariance function. And I think the formulation that they use, especially with the regression framework, is very neat. What would happen if we let this rho parameter that's in the modified covariance function, what if this ends up becoming a Gaussian process that varies in space? right? As opposed to a fixed set of regression components. There could be cases of this, so this is just a thought that I had. Next is if one wants to model cross correlations across subjects and time, right? Right now, the study indexes our observations or our observational data sets from I equals 1 through n, which combines time points and the subjects. And it does assume some independence across time. Now, let's say we want to turn this into a spatiotemporal model that explicitly models spatiotemporal dependencies. Maybe extensions into that could be interesting. It would be computationally more demanding, but I'm sure there are ways that one can remedy that by either using more cores or making the maybe you can partition the space-time domain now instead of the spatial domain. And then finally, when looking at the computational costs, are there ways that we could dynamically or optimally select key settings, such as the number of resolutions M here, or S, which is the number of points in the highest resolution subregion, or Kmax here? Right now, in the manuscript, the authors provide very nice guidelines and recommendations for these selections, but I still think that maybe dynamically choosing these after some pilot runs could be helpful, and it may take some of the decision making out of the practitioner's hand. But overall. So overall, these are my thoughts on some extensions, but I'd like to thank Emily for a really great presentation and her group for putting together this very nice study. Thank you. And then
It's a summary and also great insights into this extension. So I'll give Emily a few minutes to briefly respond to these discussions, and then we can open up the floor for questions.
Well, thank you so much, Ben. I really appreciate your thoughtful discussion, and I feel that maybe I should have let you present first. I think you highlighted some of the points from my paper really well, so I really appreciate that. I particularly find it really interesting, this idea of the binary spatial regression model, and trying to leverage maybe some kind of dimension reduction of those random effects and figuring out how to then simply model those particular lower dimensional structures. I think that sounds quite promising. I guess I don't have a firm sense of where the computational burden primarily lies here. Is it really estimation of the omegas? And then what are the particular challenges that already exist with kind of this particular reduction, and how might those be bypassed through the divide and conquer technique? But I think that sounds really interesting and a really promising area of future work. And then the other thing I wanted to comment on, which I think you hit the nail right on the head, is your last comment about choosing the different I guess I'll call them parameters, right? They're a form of tuning parameters, choosing the number of resolutions, the number of points in the highest resolution, as well as the maximum number of partitions. I think that this is something that I would love to figure out a way of doing this in a more automated way. I think that there needs to be some input from the investigator, primarily depending on the biological problem, biological or insert whatever type of problem you're looking at, but maybe designing some kind of informative priors for these and then figuring out how we might select them. I think that would be a huge contribution and incredibly valuable. And I would be really excited to see that. So yeah, thanks very much, Ben. I really appreciate it.
Great. Thanks, Emily. Any questions from the audience?
Feel free to use the chat feature or the raised hand feature if you have any questions.
Yeah, I also want to mention that, after the talk, you also have the chance to connect with the speaker as well as the discussant directly, if you will. So in the interest of time, I guess we can quickly wrap up. So Peter, you want to?
Yes, happy to do that. And I have a little little information to share, so let me set this up. Thank you, Emily. That was an excellent talk. I really appreciate it.
Thanks.
Here we go. So you should all now see a slide related to the next Journal Club. But on behalf of the chair and our speaker and discussant, I'd like to thank you all for joining us today for this Journal Club. For the next Journal Club, we will be trying something special. As some of you may know, we celebrate the best paper from a particular year, one of our journals during our biennial International Biometric Conference. But unfortunately, due to travel issues this past December with some of our speakers, the best paper session for our journal Jabez could not be held. So we have decided to host the best papers for the Jabez Awards as a virtual session, and for that session to be merged with the next Journal Club, which is taking place in March. So you can see our winning papers on the screen. Congratulations to our winners, and we will be expecting the sessions to be held either on March 20th or 21st at 11 Eastern in the US and Canada. That's pending speaker availability. We're just double checking that now. So please plan to join us then. And members will receive more information as soon as the date is confirmed. We will also be offering IBC attendees the chance to join us that day because it's an official session of the International Biometric Conference as well. So we hope you can join us then. But as a reminder, a recording of this session will be available next week on the IBS website under the Education navigation. And we invite you to add your comments or send a message directly to Emily through the IBS members community. That's available to everyone 24/7, and all it takes is your membership. And all of you who joined us today are members, and we appreciate it. But thank you for joining us. I hope you all enjoy your weekend, whether you like snow or you don't. And you may now exit the session. Thanks all.
Thank
Thanks
you.
very much, Peter.
Thank you.
Thanks, Jen.
Thank you.
Thanks. Take care. All right. Have a nice
Bye.
week. Bye.
You too.
Thank you, Ryan.